Before World War II, aviation faced a problem that could not be solved with more power. Aircraft engines were strong, but strength was not the issue. The danger came from instability. Pilots had no reliable way to control how power was delivered as conditions changed during flight. Takeoffs overloaded engines, climbs damaged components. High-speed dives destroyed engines through overspeed. Even experienced crews lost aircraft without being shot at. Engine failures were not always caused by combat. They were caused by uncontrolled force. Aircraft behaved differently at low speed, high altitude, or during steep dives, yet propellers remained mechanically fixed or manually adjusted with limited precision. Pilots were forced to manage risk instead of controlling systems. A single mistake in propeller setting could cost an engine or an entire crew. This limitation placed a hidden ceiling on aviation performance. Faster aircraft were useless if engines could not survive changing flight regimes. Long-range bombers were unreliable if a single engine failure meant loss of control. Before aviation could dominate World War II, power had to be regulated, not increased. Frank Caldwell addressed this invisible problem. He did not design a new aircraft or a stronger engine. He built the system that decided how power was released, adjusted, and restrained in real time. His work turned raw engine output into controlled force. Without it, modern combat aviation would not have been possible. Frank Caldwell was an engineer at Hamilton Standard, an American company specializing in aircraft propellers. Unlike aircraft or engine designers, his work did not focus on external shape or raw power. He worked on the critical interface between the engine and the air, how power was transmitted and controlled. During the 1920s and early 1930s, aviation advanced rapidly, but a fundamental problem remained. Engines became more powerful, while propellers stayed mechanically limited. Most aircraft used fixed-pitch propellers or rudimentary manual adjustment systems. A propeller optimized for takeoff became inefficient in cruise, while a propeller suited for speed could destroy an engine during a climb or a dive. Pilots were forced to manage this compromise constantly. They had to anticipate changes in engine speed without reliable mechanical assistance. Incorrect settings caused overspeed, accelerated wear, engine failures, and, in some cases, catastrophic breakdowns. This problem did not depend on pilot skill. It was structural. Caldwell understood that aviation could not evolve as long as this limitation remained unresolved. Increasing engine power without controlling its delivery only amplified risk. The true bottleneck was not available energy, but the inability to use it stably across all phases of flight. At Hamilton Standard, Caldwell focused on developing a constant speed propeller system. The goal was not to increase performance, but to maintain a safe and optimal engine RPM regardless of flight conditions. This required a mechanism capable of measuring rotational speed and automatically adjusting blade angle in real time. The core of the system relied on a mechanical and hydraulic governor. This device detected any variation in engine speed and instantly modified the propeller pitch to compensate. During climbs, the system adjusted the blades to prevent engine overload. During dives, it prevented destructive overspeed. The pilot no longer had to guess. The system regulated. Caldwell also worked on a critical function known as feathering. In the event of an engine failure on a multi-engine aircraft, an uncontrolled propeller would continue to spin in the airflow, creating massive drag. Feathering aligned the blades with the airflow, reducing drag, and allowing the aircraft to remain controllable on one engine. This work was not spectacular. It was not visible from the cockpit, and even less from the ground. Yet, it fundamentally changed aircraft behavior. Engines became more reliable, critical flight phases became predictable, safety margins increased without adding structural weight or complicating pilot workload. On the eve of World War II, these systems began to be integrated into combat and transport aircraft. Without drawing public attention, Caldwell had removed a technical limit that had constrained aviation since its beginnings. When the war began, the solution was already in place. Before aerial combat intensified, power. Control had been solved. Aircraft could take off more safely, fly farther, survive engine failures, and support more aggressive mission profiles. This change was not credited to a battle or a pilot. It came from an invisible system designed to prevent aviation from destroying itself. When World War II began, the systems Frank Caldwell had developed were no longer experimental. They were already integrated into frontline aircraft. This timing mattered. Aviation entered the war with engines more powerful than ever before, but without Caldwell's control systems, that power would have destroyed reliability instead of improving it. Fighter aircraft faced rapidly changing flight conditions. Takeoff required maximum thrust. Climb demanded sustained power without overheating. Combat maneuvers pushed engines across wide RPM ranges in seconds. Dives created extreme overspeed risks. Before constant speed propeller systems, pilots had to manage these transitions manually, often with delayed or imprecise control. Caldwell's system removed that instability. On aircraft like the Spitfire, constant speed propellers transformed performance without changing engine output. Acceleration improved. Climb rates became consistent. Engine stress dropped. Most importantly, pilots could focus on combat rather than engine management. This change occurred just before and during the Battle of Britain, where reliability and responsiveness mattered as much as raw performance. The impact was even greater on multi-engine aircraft. Heavy bombers such as the B-17 Flying Fortress depended on precise engine balance. A single engine failure could destabilize the aircraft if the propeller continued to windmill, generating massive drag. Caldwell's feathering system solved this problem directly. By aligning the propeller blades with the airflow, drag was reduced, allowing aircraft to maintain altitude and control. This capability saved aircraft and crews repeatedly. Bombers returned from missions with engines shut down, damage sustained, and formations broken. Little tied to destination, yet still controllable. Without feathering, many of these aircraft would have been lost due to asymmetric thrust and uncontrollable yaw. The difference was not pilot skill, it was mechanical control. Transport. Aircraft benefited in the same way. The C-47 Skytrain, derived from the DC-3, relied on constant speed propellers for safe operation under heavy load. Takeoffs from short or improvised airfields demanded precise power regulation. Feathering allowed continued flight after engine failure during critical phases. This reliability made large-scale airborne operations possible. Caldwell's systems also reduced training complexity. Pilots no longer needed to manually calculate optimal propeller settings across every phase of flight. The system responded automatically to changing conditions. This reduced pilot workload and error rates, especially under combat stress. Aviation units could scale faster without sacrificing safety. Equally important was maintenance. Caldwell's designs emphasized mechanical predictability. Engines operated within safer limits, reducing wear and catastrophic failure. Aircraft remained operational longer between overhauls. In wartime conditions, this translated directly into higher sortie rates and fewer losses unrelated to enemy action. The strategic effect was cumulative. No single mission depended entirely on propeller control. Instead, entire campaigns benefited from increased reliability. Aircraft flew longer, returned more often, and survived damage that previously would have been fatal. This consistency allowed commanders to plan operations with greater confidence in air support and logistics. Caldwell did not appear in mission reports or victory tallies. His work was embedded deep inside the aircraft. Yet every successful escort, bombing run, transport flight, and emergency return depended on his systems functioning correctly. The war in the air became sustainable because power was no longer released blindly. By the middle of World War II, constant speed propellers and feathering systems were no longer optional improvements. They were essential infrastructure. Aircraft without them were obsolete. This shift did not happen through combat discovery. It happened because the engineering problem had already been solved before the war demanded it. Frank Caldwell's work did not end with World War II. In fact, its importance became more visible after the war, when aviation expanded beyond combat into global transport, commercial flight, and modern air operations. The problem he solved, how to control engine power safely across changing conditions, did not disappear with peace. It became a permanent requirement. After the war, aircraft grew larger, faster, and more complex. Engines produced more power, flight envelopes expanded, and missions demanded longer endurance. Without reliable control of propeller behavior, these advances would have increased failure rates instead of capability. Caldwell's constant speed and feathering systems allowed aviation to scale without becoming fragile. In military aviation, post-war transport and patrol aircraft relied on the same principles. Long-range flights over oceans and remote regions required engines that could operate for hours under stable conditions. Feathering remained essential for survivability in multi-engine aircraft. The expectation that an aircraft could lose an engine and still return safely became standard, not exceptional. Commercial aviation adopted the same logic. Airlines depended on predictable schedules, reduced maintenance downtime, and consistent engine performance. Constant speed propellers reduced pilot workload and engine stress, making daily operations safer and more economical. What had once been a wartime necessity became a civilian requirement. Caldwell's contribution also reshaped pilot training. Engine management was no longer a constant manual calculation. Instead of reacting to the engine behavior, pilots supervised systems designed to regulate themselves. This reduced human error and allowed crews to focus on navigation, communication, and decision-making. Control shifted from continuous correction to monitored stability. As turbine engines replaced piston engines in many roles, the specific hardware changed, but the underlying principle remained. Modern turboprop and jet engines still rely on automatic governors, feedback loops, and protective limits. Power is not delivered directly. It is filtered, regulated, and constrained to prevent damage. This philosophy traces directly back to the problems Caldwell solved mechanically. What makes Caldwell's legacy unique is its invisibility. His system does not appear in museum exhibits as a standalone object. It does not carry a dramatic name. Yet, it exists inside nearly every powered aircraft that followed. Aviation safety standards assume controlled power delivery as a baseline. That assumption did not exist before his work. Caldwell did not change aviation by increasing performance. He changed it by removing instability. Aircraft stopped being machines that demanded constant correction and became systems that could be trusted. This trust enabled long-range flight, large-scale airlift, and the sustained operations that defined modern air power. World War II is often remembered through battles, aircraft silhouettes, and famous pilots. Caldwell's contribution does not fit that narrative. His impact was systemic. He ensured that engines obeyed limits rather than destroying themselves. In doing so, he helped transform aviation from a risky experiment into a reliable instrument of war and peace. Frank Caldwell did not win victories, he prevented failures. His engineering ensured that aircraft returned, engines survived, and operations continued. That quiet reliability decided outcomes long before combat began, and it remains embedded in aviation to this day.